So what is this thing called precipitation? Everyone says, oh, that's what happens when it rains outside. What it means in terms of chemistry is very similar to what happens with weather, because when you get precipitation, stuff falls. Snow, which we're all tired of, rain. Sometimes it rains frogs in places. You probably heard of that. Anyway, those are all forms of precipitation. As far as chemistry is concerned, precipitation is what happens when stuff won't dissociate. What do we mean by that? Here's an example. If we have your standard ionic compound, everyone's pretty familiar with sodium chloride, and it's a fairly common compound, and we know that when we put it in solution, it dissociates. Now, when you're questioning yourself about this, does sodium chloride really dissociate? Salt water is full of dissociated sodium chloride, so you don't really need to think too hard. But there is some things that just won't dissociate, and it gets kind of weird, because if we were to put together what we call a double displacement reaction, do you guys remember those? A double displacement reaction where we take AX plus BY yields AY and BX. And we had these two compounds in the reactant side, and they were both dissolving quite well, dissociating quite well. That's what this little AQ means. This stands for aqueous. That means that it dissociates. If we were to put together this double displacement reaction where we get this swappage, every once in a while you get a situation where one of these products doesn't dissociate. We call that a precipitate, and literally what happens is when this reaction takes place, it just falls out of solution and lands on the bottom of the flask. Let me show you what we're talking about. This is one of my favorite reactions. So here we have two very ionic compounds. Remember, if you're in doubt if the compound is ionic, just say the name. So, and now since you guys are all experts on calculating concentrations, you know what that capital M means. On the left, we have a 0.0075 molar solution of lead nitrate. On the right, we have a 0.1 molar solution of potassium iodide. And let's pour some out and see what they look like. And so obviously, after we've poured some out into a couple of beakers, you can see that they are both perfectly clear. So these are solutions where both ionic compounds are completely dissociated. Now, what we're going to do is add one to the other, and that's going to start our double displacement reaction. So let's zoom in a little closer. So this is our potassium iodide solution, and as you can see, even close up, it's perfectly clear. And we're going to start this reaction in a very technical way by pouring the other, which is lead nitrate, straight into the potassium iodide. And what we get is this fascinating bright yellow cloud. This is our precipitate. One of the products of this double displacement reaction is not soluble, and it turns into this bright yellow solid. And if we let it sit for 5 minutes, it'll fall all the way to the bottom. Let's take a look at what's going on at the atomic level. So we'll get to the mechanics in a little bit, but what's really neat, I think, is that this color, it's one of my favorite colors, this bright yellow. Let's get a better picture of this. This picture is a little bit better. The lighting's a little bit better. This was a really popular color back in the 1980s, and people loved to put this color this bright yellow on very expensive exotic cars of all things. So I'm going to offer you an extra credit opportunity, everybody. If you want to earn an A in the second semester of chemistry, whether you're in honors or in general, then I would like you to buy me one of these. Are you ready? There we go. Now we are talking. This is a 1982 Ferrari 308 GTSI. I stands for fuel injection, and that was the first year this was available on the 308. And they canceled it a couple years later to make the 328, so it's a pretty rare item. And in this color, please. Oh my. All right, let's get back to the mechanics. So let's remember that the two ionic compounds that we reacted were lead nitrate and potassium iodide. And let's remember that this is a double displacement reaction, which means the products are going to be AY and BX. So let's put that together. That's A, that's X, that's B, that's Y. So AY is going to be lead iodide. For those of you that know how to write formulas, this lead has a charge of +2. We know it from doing our reverse drop and swap. And iodine has a charge of -1, so we'll need a little 2 there. But for general chemistry, I'm not going to make you worry about that. And the other product is something called potassium nitrate. And we need to balance, so I'm going to put a 2 there and a 2 there. We're not worried about that. What we are worried about is one of these two products is no longer aqueous. One of these is what we call a precipitate. How do we tell? So I'm going to give you guys a handy chart. So here's how we determine what is going on in this reaction and which of these two products is our precipitate. Obviously, we know going into the reaction that the two reactants are aqueous. We know that. We saw that they were both perfectly clear solutions. One of these two products, however, is going to be a precipitate, meaning it is no longer aqueous. So which one is that? Let's take a look. It says under this general solubility guidelines, and what we want to do is identify what is inside each of these molecules that are in our products. Let's take a look at this potassium nitrate first, because it's right here at the top. It says anything that's got potassium is always soluble. Right off the bat, that eliminates that as being our precipitate. Check it else out. It's early in the morning when I'm recording this. Anything that's got a nitrate in it, and that's this guy right here, is automatically soluble in water. So that eliminates potassium nitrate as being the precipitate. Well, let's go a little further. It says most chlorides and iodides. Well, iodine is that guy. It says that most of them are soluble except, those that contain silver, mercury, and lead. So an iodide containing lead is clearly our precipitate, and that means this guy is a solid. All right, so we're going to write a couple of equations to indicate what's going on here. So this guy right here, this equation is simply what we call the formula equation, and you guys know how to write those. Some of you do. I'm also going to ask you to tell me what's going on in solution, and this is going to be what we call the ionic equation, because this shows us what's happening in solution. In other words, this shows us everything that is dissociating. And so our reaction looks like this. Lead, whoops, I don't want gray. Let's use blue. So we have lead nitrate. Oops, that's a 3. And this is clearly in solution, so we're not going to write it like that. It's clearly dissociated. That means that we have 1 lead and 2 nitrates. The 2 comes from the fact that there are 2 of them, just like writing a dissociation equation. You guys practice that. So I'm going to put the 2 here to indicate that there are 2 of them. You don't have to indicate the charges. I just do because I'm a nerd. We also have, because I balanced this equation, 2 potassium iodides, but they dissociate. That means that 2 potassium iodides dissociate into 2 potassiums and 2 iodines. On the read product side, 1 of these products is no longer dissociated. We've already identified it from our chart as lead iodide. But the other one is still dissociated, potassium nitrate. And because it is still dissociated, I'm going to write it like this. This is called our ionic equation. It tells us exactly what's going on at the atomic level. What we notice at this level is that there are some ions that are involved in the precipitation and some that aren't. Here's what we mean. What's involved in making lead iodide? Lead and iodine. Notice how the nitrate looks exactly the same on both sides. Notice how the potassium looks exactly the same on both sides. That means these aren't doing anything. They're not changing. They're not involved in the reaction. And so we're going to call these, because they don't do anything, spectator ions. All they're doing is watching. They're not involved in the reaction, which means we can eliminate them from the final reaction, what we're going to call the net ionic equation, in which we don't include spectator ions. So, not including the spectator ions makes it a lot easier. What's involved? Lead and 2 iodines, and what do they make? Lead iodide, which is a bright yellow precipitate, like that, like that. Oh, baby. Okay, let me put together a couple other precipitation reactions that are pretty neat. Okay, here's another one. This one's pretty neat. On the left, we have a solution of sodium hydroxide, and on the right, we have a solution of copper sulfate. The copper sulfate's a little blue, but mostly clear. Just copper in solution. It's got that neat blue color. And we're just going to add them together and see what happens. So here is our perfectly clear sodium hydroxide, and let's add, by ceremoniously dumping it in, some copper sulfate. And we get this bright blue. This camera really doesn't do the color much justice, but this bright blue. Let me back off on the brightness so you can see what we're doing here. It's this neat, really neat, deep blue color. Very calming, very soothing. And that's the precipitate that we get out of the double displacement reaction of sodium hydroxide and copper sulfate. Let's go to the analysis workbench and take a look at what's going on. So let's take a look at what's going on in this one. We reacted sodium hydroxide with something called copper 2 sulfate. It looks like that. For you honors chemistry people, copper 2 means that the charge of copper is +2. For general chemistry, all you have to do is worry that that's what it looks like. And of course, this is a double displacement reaction. AX would be Y. So the products are going to be AY and BX. So what's AY? That's A and that's Y. So AY is sodium sulfate, which looks like that. And BX is going to be something called copper 2 hydroxide. Now, which of these 2 products is our precipitate? Obviously,
following teachers please come to the main office?
Obviously, we know that everything that's on the reactant side is aqueous because they were already in solution. Means that one of these two guys is going to be our precipitate. Which one? Well, here is some guidelines for things that involve hydroxide. Check it out. Here's what this means. Obviously, hydroxide's this guy. It means that hydroxide will be aqueous as long as it's paired with calcium, strontium, barium, lithium, and then, of course, here's those three from our solubility guidelines. So anything that has sodium, potassium, or ammonium is always going to be soluble. But insoluble with any other ion, I guess that means that it has to be this guy. And you're saying, well, Mr. O, what about this stuff? What about sodium sulfate? And what it says up here is that anything that has a sulfate in it, right here, anything that has a sulfate in it is soluble unless they contain these 5 elements. Well, sodium isn't one of those. That means that this stuff has to be aqueous. So let's take a look. What's going on? This is obviously our formula equation. And now we will write our net ionic equation. We know that's aqueous, and that's aqueous. That means they dissociate. So the first thing I'm going to do is I'm going to make sure that this is balanced. Boop, put a little 2 there. That balances everything. And so the ionic equation is going to look like this. And I'm spread way out because it takes up some space. We have 2 sodiums and 2 hydroxides. They came from here, the fact that there's 2 of them, and they're aqueous, so dissociates. We have 1 copper sulfate, and it looks like this. Remember, we're not going to dissociate our polyatomic ions. And our products, I'm going to scoot it over a bit here, is aqueous sodium sulfate, and there are 2 sodiums, so 2 sodiums and 1 sulfate. And the final product is copper hydroxide. That's this blue stuff. Neat color, huh? And notice how it has totally fallen all the way down to the bottom. That's what we mean by a precipitate. And a lot of people, when they write the formula, instead of saying that it's a solid, they just put a down arrow next to it because it just pops out of solution. So let's check out what the net ionic equation is doing. That means we want to eliminate all the spectator ions. Remember, spectator ions are the ones that don't do anything. They look exactly the same on both sides of the equation. That means the sodium looks exactly the same. It's not doing anything. And the sulfate looks exactly the same. It's not doing anything. What's involved in the precipitation reaction? Copper and hydroxide, which we know because hydroxides aren't soluble with any ion that isn't calcium, strontium, barium, lithium, sodium, potassium, or ammonium. So what is going to be our net ionic equation with all of these spectator ions eliminated? Check it out. 2 hydroxides react with 1 copper. You don't have to include the charges to produce 1 copper hydroxide. And this guy is our precipitate. All right? So take it for a spin, okay? I'll see you guys in the next one.